Okay, so last time we were going over this example. I took, so if you take the polynomial x cubed minus 2, it's an irreducible polynomial of the rationals. Just for shorthand, I'm gonna let alpha be the real cube root of 2, one of the roots of this polynomial. Omega is a primitive cube root of unity, so it satisfies these equations here. Omega squared plus omega is 1 is 0. Omega squared is equal to the complex conjugate of omega, which is minus 1 minus omega. And the three roots of this are alpha, and omega bar alpha. Those are the three roots to x cubed minus 2. Now, what I want to do is I took Q and I threw in all three of these roots. This is the smallest field that contains all three of these roots, because guess what I did? I took Q and I threw in all three of those roots, right? Now notice that this is a field. And so if I have alpha and omega alpha, I have the quotient of these two. So I've got omega, right? So alpha and omega are in here, right? Alpha and omega are defined here. So Q alpha omega is contained in this more complicated. And in fact, you have an equality. You also get this big field is dominated by the alpha and omega here. You get equality. The only thing missing is I get it. I get that alpha is alpha is in here, and I get that omega alpha is in here, right? But why is omega bar alpha? Well, once I have omega in this field, right? Once I've got my omega, then I have omega. I have omega plus 1, so I've got minus omega bar, so I've got omega bar. So these two fields are in. Everybody agree with that? And so from now on, I'm just going to call this the alpha and the omega. You alpha omega. Now, notice that is the smallest field that contains this. I'm going to appeal a little bit of your intuition at this point, because we're going to shore this up later. But this is a degree 6 extension, right? Let me kind of talk you through that here. That's degree 3. We've discussed why that's true, because alpha is the irreducible polynomial x cubed minus 2. That's irreducible over Q. So just to get there, get this. Now to get all the way up here, you've got to join omega to it, right? Well, notice that the minimum polynomial over omega so omega is degree 2 even over Q, right? Now, the question is, so this means that this extension right here can be of degree 2 or less, right? It can't be of any degree more than 2. Would everybody agree that this polynomial is irreducible over Q? It has to be, because it's got complex conjugate roots that aren't real, so this has to be degree 2. It's also irreducible over this field. It's funny. It's the same reason, right? This is a quadratic polynomial. it's either irreducible or it factors into two linears, right? And if it factors into two linears, that would mean it would have to have the roots here. But the roots are complex and not real. So this thing persists in being real. The degree 2 and 3 polynomials are often easier to handle this way. This is actually a degree 2 extension. And we know that the extensions are multiplicative, so this, in some sense, justifies this statement here that it's degree 6. Right, okay, so far. So let's take the roots. So here's my worksheet over here. Alpha, omega alpha, omega bar alpha. I'm gonna call it 1, 2, and 3. Because what I'm trying to do is I'm trying to find automorphism. Q alpha omega over Q. Now, I've taken the easiest one. Now, what we've learned so far is this polynomial is irreducible. And any automorphism of this field here must take a root of this polynomial to another root of the polynomial, right? So any automorphism has to commute these three roots. And if you look at the basis, once I tell those three roots where to go, I've completely determined the action on the basis. So that means one thing is kind of striking. There are at most 6 automorphisms in this field. Why is that? Because there are most 6 permutations of those three roots. Every one of them potentially gives a different automorphism. It's conceivable that they might not. That 2 permutations might or that some of the permutations might induce the same automorphism, but there's at most 6. Everybody agree with that? Let's go through it. I think we did it this one last time, 2, 3. So my notation here is, let's try to induce an automorphism by swapping roots 2 and 3. Now, one obvious way to swap roots 2 and 3 would be an automorphism of this field that I'm sure is an automorphism. It's complex conjugation. I know the complex conjugation is an automorphism of complex numbers. When you restrict it down to here, it's an automorphism. When you restrict it to the reals, it's an automorphism too, but it's silly because it's only the identity. Here you get something genuine. Well, omega squared alpha. So I'll use the notation here. And this thing goes to omega squared alpha squared. And omega squared is alpha. Let's see what happens if we try to swap 1 and 2. Alpha goes to omega alpha goes to alpha. Well, we need to, in fact, it'll help you write this down separately. Alpha goes to alpha omega, and omega alpha goes to alpha. Let's see what happens if I just do this. Any such automorphism, if you take omega alpha to alpha, I'm sorry, if you take this here and this here, then the quotient of these two, which is omega, must go to the quotient of these two, which is 1 over omega, which is omega squared. So let's see what this does. This, of course, takes 1 to 1, as all the automorphisms should. This takes alpha to omega alpha. And it takes omega to omega bar. Well, omega squared, I'll write it this way. So what does it take alpha squared to? Well, if it takes alpha to omega alpha, then it took take alpha squared to omega squared alpha squared, right? And now get this thing totally beat, because if alpha goes here and omega goes here, then omega alpha goes to alpha, which actually I just recovered what I was supposed to get, right? And it should take alpha squared goes here and omega goes to omega squared. So this thing goes to omega squared. So this goes to omega alpha squared. Everybody okay with that so far? Okay. Let me do the other element 42. This one should swap alpha and omega squared alpha. Thirdly, yes. Alpha and omega squared alpha, and should take omega squared alpha. So again, this goes here and this goes here. So omega squared quotient here must go to 1 over omega squared, which is omega. Which means if you square this again, this means omega goes to omega squared. So once again, this one takes omega to omega squared and takes alpha to omega squared alpha. Let's see if I can get what I got. Okay, where does this take alpha squared to the square of that? So this is omega fourth, which is omega alpha squared. This takes omega alpha to omega alpha. And this takes omega alpha squared to alpha squared. Any questions on that? Now, we've done 4 out of 6 possibilities. Notice that they've all given us something different. These two are definitely distinct. These two are distinct. These two are distinct. And these two are distinct. Now, in this one, I'm trying, omega has to go to omega alpha. Omega alpha goes to omega squared alpha, and omega squared alpha has to go to alpha. So it does that 3 cycle among, I'm sorry, this should be alpha. Alpha goes to omega alpha goes to omega squared alpha gets alpha. So the quotient of these two, this gives me that omega goes to omega. Right? That's convenient. I'm gonna say this is 1, this goes to omega alpha. The square of this goes to omega squared alpha squared. And now I just have to put together the rest. Alpha omega, now go to alpha omega squared alpha. And omega alpha squared should go to alpha squared. The last possibility for permutations is the inverse of this one. This one takes alpha to omega squared alpha, omega alpha. Uh, Omega alpha goes to alpha, and omega squared alpha goes to omega alpha. Okay, good. Let's see what this one does. Taking the quotient again, omega goes to 1 over omega squared, which is omega. So this one also fixes omega. This goes to omega squared alpha. Right. So this one goes to the square of this, so this is omega alpha squared. And again, put these together. This one should go to alpha. And this last one should go to wherever omega alpha squared goes to, so that should be omega squared alpha squared. Any questions on that? You all see how I'm getting all of this? Notice that all of these are different. And they induce a map on the basis that's actually a field automorphism as well. Let me point out a couple of things here, though. Yeah, I want to talk a little bit further about this example. Because as I promised, I think that a big chunk of the fundamental theorem of Galois theory is contained in this example. Those are the between right here, venture. Yes, it is. How many fields are there between Q and join, between Q and join power? Leads, right? I mean, why can't there be infinite, right? I mean, certainly Q is an infinite field. This is an infinite field. Let me ask you. So this is but this is where I would start. I'm kind of a ringy guy. I like the fields, I like the rings. In fact, in that regard, you may refer to me as Sauron. But let me ask a simpler question. How many that's 3. Now, see, that one I can wrap my head around because I don't know much, but I know there's only 6 elements in S3. I mean, look, even from a subset point of view, there's only 64 possible subsets of that, right? Or let's see, yeah, that's right. And most subsets aren't subgroups. only a few, in fact, I can tell you what the subgroups are. I can draw a little lattice, right? With, you know, my apologies to my colleague for this, but S3, you got the whole shebang. And then you got E. Ooh, boy, I'm rolling right along, aren't I? Right, now, I do remember S3 has that one big normal subgroup, or three, right? So it's got the subgroup, that's this, E, 1, 2, 3, and 1, 3, 2. This was normal in S3, and it's the only non-trivial normal subgroup, right? That's the only subgroup of S3 of order 3. I've got the subgroup of order 6, 1, 3. The only other possibilities are subgroups of order 2. How many of those are there? Any? There's actually 3 of them, aren't there? Right? There's one for each one of the transpositions, right? So I will shortcut my notation here and I'll say group generated by 1, 2, group generated by 1, 3, and group generated by 2. So you got these here. So that's what my lattice would look like, right? Of these subgroups. And let me sort of record the index. This one's of index 2. This one's of order 3, so it's index, the identity is index 3 in here. These are all of index 3 and of order 2. Right? Easy peasy lemon squeezy, right? I mean, you know, and certainly if I had said S5 and asked you for the subgroups, then there would be, you know, lots of gnashing of teeth and wailing and so forth. Be very biblical, but nonetheless, it's doable, right? I mean, you could either have a lot of patience or a good internet connection, and you're good to go, right? Because even though there's a lot of subgroups of S5, there's only 5 many. These are infinite things, so at first blush, why can't there be infinitely many fields? But there can. And in fact, I want to take a look at some, let me help cherry pick some fields. So, Jonathan, I think you said there's 2 intermediate fields, right? Okay, so what popped to mind? The big one and the little one, right? I can make that. So yeah, the big one. Center. The little one and the big one. So are there more? Name another one. You enjoy alpha. Yeah. What's up? How about it? Are there others? I mean, those are the 2 most obvious, right? Because I know I've got an alpha floating around. Yeah, alpha's one big one here. Now I've got this omega that helps it out by giving the other roots because it's a primitive 3rd root at the end of it. Now, let's go back and let's look at these automorphisms. That's another one. Of course, notice that the degree of this extension here is 3, isn't it? Right, because alpha is the root of x cubed minus 2, right? And this is another root of x cubed minus 2, so this must also be 3. Are there any more? Is it? One more. I'm sorry. One more. Alpha. We want to do that. right, no. Was this exhausting? And by the way, good job, by the way, you got at least a lot of them. But you were kind of guessing, right? You knew there was an alpha floating around, you knew there was an omega floating around, and then some clever person decided to get the alpha and omega together here, and then there's also the alpha omega squared and so forth. There's a systematic way to figure this out. Can you characterize alpha? Let's say Q alpha in terms of these automorphisms. Ah, uh, notice the following. The identity fixes every subfield. Do I agree with that? Notice alpha and alpha squared are left alone by B23, right? But everything else goes for a ride, right? Omega goes somewhere else. Omega alpha goes somewhere else. And omega, well, I guess I need alpha omega squared because it's going somewhere else. Alpha omega squared else has to go somewhere else too. Q alpha is set of elements fixed by do I agree with that? What's fixed by B12? Actually, let's start off with B13. Y'all look at the table and tell me what look at the B13. Can you give me an educated guess as to what's fixed by B13?
You would join alpha omega.
That is correct. Notice B13 leaves alone the omega alpha. And you might ask, let me add one more row to this because I am curious about the three roots. Let's look at omega squared alpha. The other root, here's omega alpha, omega alpha, omega squared alpha. Where does omega squared alpha go? Well, alpha goes to alpha. Oops. Well, actually, we'll do this in all of these. The identity goes to omega squared alpha. Here, omega goes to omega squared, so omega squared goes to omega. So what happens with omega is either omega and omega squared are left alone or they're swapped, right? I agree with that? So I can get my information I need from here. What happens to alpha? It goes to alpha. What happens to omega? It's swapped. So this goes to omega alpha. Right. What happens to omega squared alpha here? Well, alpha goes to omega alpha, and omega goes to omega squared, so this goes to omega times omega alpha, so this is omega squared alpha. So that leaves omega squared alpha alone. What happens, 1,3, alpha goes to omega squared alpha, and omega squared goes to omega, so this goes to alpha. Right? And now we've got to do these permutations here. Alpha goes to, the cool thing about this, these last two is omega is left alone, so omega squared is left alone. So alpha goes to omega alpha, so omega squared alpha goes to alpha. And in the last one, alpha goes to omega squared alpha, so omega squared alpha goes to omega alpha. There you go. So now it's clear, I think, that Q was fixed by 1,3, the roots. Well, the subfield fixed by 1,3 is just Q omega alpha. What is the subfield fixed by B12? So this column here, alpha is moved. This is moved. This is moved. Oh, look at that. Omega alpha squared is fixed. And the other root is actually, right, omega alpha squared is fixed, but omega squared alpha is fixed. Notice that this squares to this. So this is Q alpha omega squared. Now, I'm talking about subgroups here. I just picked on the element here because the only element in this group generated by P12 is P12 the identity. The identity fixes everything, so there wasn't any point in me looking at that. But here, let's look at the subgroup. This normal subgroup we found here. What's fixed by, let's just look at the last two columns. Well, it looks like alpha scrambled up, so is alpha squared. Oh, look. Omega is fixed. But it looks like everything else is scrambled up and nowhere to go. Right. What's this one? Now, I just looked at the proper subgroups. This fixed by S3.
Q.
Only Q. What's fixed by the identity? The whole thing, right? This right here is basically, this example is the heart and soul of the fundamental theorem of Galois theory. I'm going to draw more parallels here. Notice that lattice matches this one by taking the group and saying, okay, what subfield do you fix? S3, the whole thing. The identity, who do you fix? All of the field, right? Subgroup generated by 2, 3. What do you fix? Oh, I'm complex conjugation. I fix this. And there you go. It's in one of these little trees here. Notice that also the degree of this extension, Q alpha over Q is 3, which exactly matches the index of the subgroup, in this case 2, 3, inside of S3. The indices match here. Well, now, I'll give you a shiny buffalo nickel though, if you can tell, there's one other property reflected in here, see if I can see it. So we've got the lattices, we've got the matching indices versus degrees of field extensions. This basically is it. You have correspondence between subfields of a Galois extension, which I'll tell you what that's all about in a moment, and subrings or subgroups of the Galois. There's one other extra property in here that we haven't talked about. Can anybody identify another? We talk about indices and the lattice or whatever. There's another property in here that might be of consequence.
Maybe one of that something is normal.
That's exactly
Maybe
right.
say something about Q one.
That's right. The normality, the subgroup is normal. The normality of this says something about the status of this field here. It turns out that this field extension is nicer than these in the following sense. This extension is generated on omega, where omega is a root of that polynomial, right? This extension has the property that it is Galois, and I'll be more specific about what that means, but for here, maybe the easiest thing to think is when I join omega to this one root, I automatically get the other, right? Because the two roots of this are omega and omega squared, which is minus 1 minus omega. Those are the two roots of this. If I join one root to that field, I automatically get the other, right? This does not happen here. This is the root of, say, this is the real cube root of 2. I don't automatically get the other roots that way, right? And that's essentially what the normality is telling. That's really fast and loose, and I will make this more precise as we go along. But any questions so far? This is a good example to keep because keep in your mind, because like I said, a lot of what goes on in fundamental Galois theory is contained within this example. Let's look at a couple more. The next example is sort of designed to show you field can matter. Example. Oh. Yeah. All right, so let's look at polymorphism. First, find smallest extension. And then you all 4 of these roots. Right, this has 4 complex roots. How would I do that? Right, well, let's figure out what, in this particular case, I can actually figure out what the roots are, and I'm X is 4. which is four is -1, which in this notation is e to the I. So x is e to the I power 4 is I over 2k, and of course that's a wildly repeat, so I get the roots really e to the power 4, e to the I 3 power 4, e to the I 5 power 4, e to the I 7 power. We're going to do some stuff that will make this example a lot easier later in this section. But anybody want to guess? So there's an easier way to think about this. Actually, let me. Alpha to 4 is -1. And this field is actually Q. And actually, there's a lot of redundancy here. This money is one. Right. By the way, it's interesting to notice that this extension also contains I, doesn't it? Because the square of this is I. Agreed? This is actually Q adjoint of alpha. Right? Because I mean, we're talking fields here, baby. If I've got alpha, then I have all powers of it, right? So a lot of this is redundant. And in fact, it really shouldn't matter which root I adjoin, right? What happens if I look at Q adjoint with alpha cubed? Well, if you've got alpha cubed, you've got alpha cubed squared, right? Which is alpha to the 6. Well, I shouldn't do it this way. If you've got alpha cubed, then you've got alpha cubed to the 3rd power, which is alpha to the 9th, which is alpha. Everybody agree? Because alpha A is 1. So if you've got Q adjoined with alpha cubed, you've got Q alpha start over. If you've got Q adjoined with alpha 5, you've got Q adjoined with alpha to the 5 squared, alpha to the 5 to the 5, which is, and of course 25 is also alpha. So no matter what root you adjoin, you get this. What is the degree of the extension? Because that original polynomial is just right. Anybody want to know, guess what the Galois group is? That is the group of automorphisms at fixed Q. I think you can probably find these by hand. Galois Q alpha. Now remember, we're still learning this notation. This just means the automorphisms of Q alpha to fixed Q. Now, I don't know much, but I do know this. If phi is in the Galois group of Q alpha over Q, then phi of alpha, I'm sorry, phi of S alpha is what? Or what can we narrow it down to anyway?
One of the other roots.
It has to be one of the other roots. So this must be. Right, okay with that? Let's go through the cases. The alpha is alpha. And that means, of course, this is the identity function here. Takes all powers of alpha to the corresponding. What if phi alpha? So alpha goes to alpha cubed. Where does alpha cubed go? That is correct. It goes to alpha cubed cubed, so it goes to alpha 9, which is alpha 9 is alpha. What about alpha 5? Alpha 15, which is alpha 7. Where does alpha 7 go? Alpha 21, which is alpha 5. So it looks like in this case, choosing alpha to go to alpha cubed determined where everything went automatically. What happens if phi of alpha is alpha 5? Alpha cubed now goes to alpha 15, which is alpha 7. Alpha 5 goes to alpha 5 squared, alpha 25, which is alpha. Should be. And I'll bet you a nickel, this goes to alpha cubed. 35 mod 8 is. My last choice is alpha. That's the only other place you can go. There's only 4 roots. Itself, alpha cubed, alpha 5, alpha 7. Has to go to, well, alpha goes to alpha 7, which by the way is alpha inverse. So this is actually the function that takes everything to inverse. So alpha cubed better go to alpha 5, right? And alpha 5 better go to alpha cubed, and alpha 7 goes to alpha. And that's it, because I've exhausted all the possibilities. So there are only 4 automorphisms, right? The identity in these other 3. What's the Galois group here? In order 4, it can only be cyclic in order 4 or Z2, Z2. Notice that every one of these automorphisms is orders here. Right, and you compose it with itself, right? Alpha to alpha cubed back to alpha, right? It just does a 2 swap. In fact, if I number these roots, 1, 2, 3, 4, this one is permutation 1, 2, 3, 4. This is the permutation 1, 3, 2, 4. And this is 1, 4, 2, 3. And of course, I left out the identity because the identity is critical. This is the Klein four subgroup of, and in fact, it's the normal Klein four subgroup, that's 4. Okay, anybody okay with that? So I will leave you with 2 questions. In the Galois group, for Q alpha over QI. And what if original field is Z mod 2 instead of. So in other words, do this problem again with x4 plus 1 being over this field instead of being over the rationals. See what you come up. Okay, any questions? Questions on that? All right, well, I'll see you guys on Friday. Hopefully, you can come